Hi, so this is a new talk. This is the first time that I've done this, so please don't hesitate to ask questions, make suggestions, either during the talk or afterwards. I've been doing Scala 10 years now. I've been on the Scala team at Lightbend since 2015, and I've been living here in San Francisco for about a year and a half. My qualifications for talking on this topic, this is going to be based on two experiences that I've had in my career. One is that for many years, for more than a decade, I was the lead developer on a large, initially all Java, later mixed Java and Scala codebase. So this was already a legacy codebase that I inherited even when I started, and then I had to keep it alive over a course of many years. So I hope that I learned something about how to improve the health of a codebase over time. And the other experience that this talk is based on is that in 2016, I built, with the help from some of my teammates at Lightbend, a tool called Sculpt. And I'll explain a little more later what that is. There's two possible ways or two possible reasons this talk might interest you. One is that any Scala programmer is using tooling. This is a talk about tooling. I'm presenting. We'll see as this develops that I'm presenting an area where the tooling that exists for Scala is not that strong. There's some, but it's not like super well developed, super solid. So I also hope to inspire people who are building tooling, either for the Scala community or just for use on your project or within your company, to provide some inspiration on that. So taming tangled code. We all like clean code. We'd like to achieve clean code. Clean code, of course, looks nice. It's well formatted, but it should also be well structured at a deeper level, not just at the level of does it read well line by line and method by method. There are different things we might mean by well-structured code. I'm going to focus on a particular meaning of that. Which is the internal dependency structure of code. This is, so when I say dependency, I'm not talking about external dependencies. I'm not talking about libraries you're pulling down and throwing on your class path. This is about your code. And so when I say dependency, I'm talking about one place in your code that depends on, that refers to another. And that does it at compile time. So this is all about compile time tooling. Our goals in wanting to improve the dependency structure of our code are modularity, which I hope I won't unpack too much why that's good, but it has like all sorts of benefits. There's so many. Modular code is more readable. It's more comprehensible. It's more maintainable. And it's also it can also serve different purposes. So often the motivation for improving the modularity might be, of your code might be to split out some functionality so you can use it. You can use it elsewhere. Even if you aren't doing that, you might like to improve the dependency structure of your code just because you'd like it to compile faster. And that was actually I think the major motivation for the customer who funded this work at Lightbend. Incremental compilation in Scala is driven by the dependency structure of your code. If I change a piece of code, the stuff that has to be recompiled is everything that depends on the piece of code I just changed recursively. So a simple picture of what's good and bad in dependencies. The best situation is that you have two pieces of code that are entirely decoupled and can be compiled and developed completely separately. Next best is a one-way dependency, and the thing that we really want to avoid is circular dependencies. And circular dependencies are a bigger problem the larger the grain size of the code that we're talking about is. So two functions that mutually depend on each other, that's probably fine. Two source files that have circular dependencies between each other, getting more questionable. On any project I've ever worked on, I've never allowed circular dependencies between packages at all. I think that's a really strong smell, and we know that at the binary dependency level, that circular dependencies are just impossible. I mentioned that I worked on a large tangled code base for many years. I was unable to dig deep enough to get a diagram of the dependency structure that I started with. But suffice it to say that basically everything depended on everything else, directly or indirectly. It's remarkable how few. It's remarkable how few bad dependencies can create a situation like that. You can have code that's kind of mostly modular, but then there's that one place where this class just reaches into this other class. And there's some math in graph theory that will tell us that you don't need to do that very often before you literally have the situation where everything is mutually entangled. So this diagram on the right is dated 2013. I show people this diagram not knowing if they're going to be impressed or horrified. Like, oh, that looks nice, or oh my God, that looks, what, wow, what a mess. I encourage you to see this diagram on the right as good compared to where we started. So each of the nodes in this diagram is a package. There are no cycles between packages. Although some of the details in this diagram can get messy, there's a clear overall macro structure. This is a layered architecture separated by the dotted lines, where each layer has direct dependencies only on the level below. If you look even more closely at this, you'll see that there are clusters of nodes that have no incoming arrows. So that's great. There's whole modules and collections of modules here that no other code depends on at compile time. All of this code is working together at runtime, but I can, anytime something has no incoming arrows, I can recompiling it has no. I don't need to recompile anything else. And this structure was actually enforced by our CI. So you could not check in something that violated the structure without some automation complaining at you. There's a danger when you're doing this kind of work that you lose track of that it becomes all about boxes and arrows on paper, and you're just like architecting and forget what it's about. But the modularization that we did on this code base was actually about business goals and about features. So there were features that we wanted to do that required the modules to be separate. We had an authoring environment that needed to be separated from a runtime engine, so the runtime engine could be delivered, could be lightweight and embeddable. This began as a GUI application. We wanted to support command line operations, so all of that code had to be disentangled. And then we wanted to make modules so we could open source them, although actually the whole code base is open source now. And we wanted to run some of the code in the browser on Scala.js, so that required making that code completely independent and removing all of its, getting all of the Java code, since you can't just throw Java code into a Scala.js application. So we had to make it pure Scala. So these are, this was really, this kind of work can actually be kind of life or death for a code base. Like, can it evolve to suit new needs? You can do this kind of work of disentangling code by hand, certainly. But it's really a lot easier if you have some tooling to help you. And there's two possible approaches that tooling for dependency analysis can take. You can have a tool that looks at the bytecode that comes out of the compiler and looks at the dependency structure of the bytecode. Or you can analyze the source code and try and pull the dependencies out of that. Source code analysis is, I think, definitely preferable. There are, particularly if you're interested in reducing compile times. So you can have dependencies in your code that the compiler sees that don't actually leave a residue or an effect in the bytecode. So you could fix up the bytecode without actually fixing all of the all of the problems that are having tangles in your code. So I think ideally we would prefer source code analysis, but bytecode analysis is pretty good, and it has the great advantage that it's language independent. So tools that work on Java bytecode, most of them will work as expected on the bytecode that comes out of the Scala compiler, even if the authors of that tool weren't anticipating that. So I'll show the bytecode tools that I'll show come from the Java world, but just happen to work in Scala. So these two tools for bytecode analysis, one of them I think almost everyone who does stuff on the JVM has heard of, and that's ProGuard. The other seems to me to be quite obscure, so I don't think I've ever run into anyone who knew what it was. So part of my goal with this talk actually is to raise awareness of this tool Classycle, which I found incredibly helpful in my own work on my own code, but people don't seem to know about it. Both of these are very, very mature, stable tools. They haven't changed much in recent years, but both of them were updated to add support for Java 8 and for Lambdas. So there's somebody there keeping the lights on and making sure that these things keep working, even though they aren't changing much anymore. And then we'll come back to for the tools for source code analysis. I'll show a tool by Howie Lee called Acyclic, and then Sculpt, which is the thing we built at Lightbend. So by doing source code analysis, I think we can expect higher fidelity, but the tooling is less mature, less finished. Okay, so Classycle, this is an open source tool developed for Java. I never had a problem using it on Scala bytecode. It always works fine. What it does is it's just a jar that you point at the directory or jar that has your class files, and it analyzes everything anywhere in the class file that refers to anything else, and then collects that raw data. I'm not actually sure if it makes the raw data available. What I always used was a report that it can generate. And this, I put a screenshot on here in case I wasn't able to show the user interface, but it's better if I can actually show the UI live. So what you get out after you run this on your code is there's a few sections here. There's some summary statistics at the top. There's a list of cycles. So these are, I said in my code that package cycles are forbidden, but class cycles within the same package I think are usually okay. So we've got 54 class cycles, and it will show you, you can see what the classes are in it, and get some other statistics and zoom in. Layers. Okay, so this is helping you understand the structure of your code by grouping it into layers. Layer 0, those are the classes that can be compiled purely by themselves without reference to any other code. Level 1, so then once you've compiled level 0, what else can you now compile? That's level 1. Everything in level 1 refers only to level 0 classes. Let's see, does layer 1, in layer 1 are you allowed to refer to other layer 1 classes? I think you are, and so forth. So, and again, this is something you can zoom into. You can see what all the classes are in a particular layer. So at the bottom, we see lots of these are usually interfaces and little utility classes. And then when we get all the way up at the top level, it's like the big master class that glues your whole application together. And then yes.
Does it get any finer grain so that you can tell exactly whether it's a method call or something else that's using a particular class, or is it just at the class dependency?
Please repeat the question.
Sure. So the question is about granularity. If this is telling me that class A depends on class B, can I get any more detailed information on where exactly that dependency is coming from? Like, is it in this method? So let's use this last section, and this is the big section that goes all the way to the end of the page that just lists all of your packages and all of your classes. So we can look at the agent class, uses internal, and it looks like this doesn't give you method level granularity. I'm a little hesitant to say for sure that it doesn't, but I don't remember using it. There was Yeah, to make sure I'm answering that question correctly, I have to look it up afterwards. I don't think it's in this UI, but I think the command line tool might actually do it, and I'll show the command line tool also. Okay. So that is Classycle. And in the interest of time, I should move on and just show you one more thing about Classycle, which is that it's also exists as a command line tool. So this is something that you can actually make part of your build if you want. And this is how we actually enforce this structure in the CI on this project. So to use the command line tool, you write a config file that has a bunch of rules in it, and these are a few sample rules. The keywords here are independent of and directly independent of. So you can specify that this package is it can depend indirectly on something else, but it's not allowed to talk about it directly, right? So that would be directly independent of, and then independent of is the stronger predicate, which is like, no, you can't have this stuff anywhere in your recursive tree of stuff that you depend on. I'm including ProGuard just briefly. It might be, so ProGuard, we mainly think of it as a jar shrinker and optimizer, but in order for it to do that work of shrinking a jar, this analysis of dependency structure bytecode, it's exactly what it's doing, and it's really good at it. ProGuard is this thing that everybody uses. It's been around for years. It's like it's bulletproof. So whether ProGuard is a possible basis for more sophisticated tooling in this area, I don't know, but I have definitely used it as a backstop. Like, okay, I think I've got things modularized, and now I'm going to tell ProGuard to make a jar that just isolates something, and if there are any dangling references in that jar, ProGuard will find them and complain. It's really good. Okay, any questions on the bytecode before I change gears and start talking about source analysis? Okay. So the source analysis tools that I'll talk about are Scala specific. The first one is in this space was built by Howie Lee, who I think people who've been at SF Scala for a few years anyway know well, and that everyone involved with open source Scala knows well. So this is something that he built for himself and uses in his own projects. So it's based on similar technology as Sculpt that we're going to see next, but it has a much more focused goal, which is he specifically zeroed in on preventing cycles in your dependencies. It's a compiler plugin. It operates by putting this special magic import in the source files that you want processed, or you can also just say process all the source files. And you specify whether you are happy with the looser rule, where cycles are only forbidden at the package level, or whether you want to enforce something much stricter and disallow cycles even at the level of source files. I don't think it does class level, and I think that's probably sensible. Like, I'm not sure you would ever. It seems perfectly normal to me to have a cycle of classes in a single file. And if your code, when the plugin runs, if it does find cycles, then you get a nice detailed report right down to the level of the particular line of code each line of code that's actually participating in the cycle that you find. So this is a terrific tool, but it is somewhat special purpose. Okay. And now I'll talk about this thing Sculpt that we built at Lightbend. So this was developed for a customer who wanted it, but also I think we always assumed and expected that we'd make it available as open source as well. So I did most of the work on this, but Adrian Moores, did the most difficult of the compiler wizardry that's in here. And then Stefan Zeiger, also on the Scala team, did some of the coding as well. So we just open sourced this last month. And I'd put the like a maintenance status slide last, but I think I'm going to cover this now actually, so you know what you're getting when I start describing the technical details. So this is not actively supported and maintained, but nor is it completely abandonware. It's somewhere in the middle. So there's a key component here that I'll talk about in a little more detail called ExtractDependencies that actually generates the raw dependency data from the compiler. That piece is very much not abandonware. So that's a piece of code that was hard to write. It would have been difficult for someone outside our team to write it, I think, without a lot of study. And it's like a possible nucleus or kernel for all sorts of possible tooling that you could build. So that piece of it, if anyone wants it, it's like if we're not going to be hacking on it unless people step forward and say, I want this and I'm willing to help hack on it and test it. But if people like that do appear, then we'll work on it with you. The rest of Sculpt is more like, here it is. If someone sends a pull request with a modest fixture improvement, I'm happy to review it. But we're not going to be doing any further major development on it. So that's the status. Yes, Will.
Do you have artifacts published to Maven and so forth?
No. So in order to build it, you have to build it from source yourself. I don't think that's a big hurdle. It's just a standard SBT thing. You clone the repo, type SBT publish local, and you're good. If there's demand to add publishing, I would merge a pull request that added publishing. Yeah. Oh, I didn't repeat the question. So the question was whether binary artifacts have been published. Okay. This is a compiler plugin like Acyclic. It's informational only, so there's no attempt to enforce any particular policy. We're just producing data that you can do what you like with. This kernel that I mentioned, the piece of code that's the key to the whole thing, is actually code that we borrowed and adapted from Zinc. If you don't know what Zinc is, it's the incremental compiler component of SBT. So it started life as within the SBT codebase, and then it later became available and published as an independent artifact so that maintainers of other build tools can add incremental compilation to their tools as well. So the Maven plugin for Scala uses it. I think Pants and Basel both use it. It's the incremental compiler. So the fact that we're using the same code both in Zinc and in Sculpt means that you can trust that the exact same information that you get from Sculpt is the same information that guides incremental compilation, and so that that's should be especially appealing to you if one of your main motives for this is wanting to reduce incremental compile times. I've put the source file. I put the URL of this kernel source file. It's some pretty hairy compiler code. I say that to tout its value, but I also don't want to scare. I don't want to scare off anyone who might be interested in trying to tinker with it. If it needs fixes, it's doable. There's most of the structure is there, and from this point forward, it should only need the most it should need is tweaks around the edges. So what does Sculpt add beyond just this kernel? So this ExtractDependencies code listens to the compiler as it's working, and the raw dependency information that's coming out of the compiler is first stored in memory as instances of case classes, and these are very simple case classes. They're just data. They're not. They have no references to internal compiler data structures. They're not in the compiler cake. It's just data. And if you'd rather have it on disk in order to deal with it, there's also code to output that information as JSON, and we'll see in a second what that JSON looks like. So that one possible use mode for this is just that you run it in the mode where you request JSON output, and then you do your own analysis of the data that comes out. We do have some fairly simple analysis that the tool can do itself. I should have said you can request for you can get the raw data at the method level, or you can ask for it to be aggregated at the class level. Both of those options are supported. I showed you in Classycle the layer report and the cycle report. Sculpt can do that as well. We copied that. It doesn't come out as a nice HTML page. It just comes out as text. But the logic for computing that is there. Alexi, how am I doing on time?
Good. I think I have about 10 minutes.
Okay, perfect. Excellent. And okay, so let's look at some sample output, and I'll switch over to the browser to show that. So the examples, this is the repo on GitHub, Scala Sculpt. And I think, well, if I do say so myself, I think the documentation is pretty good. Like the code that exists and the capabilities that exist are fully described in the README. I won't even have time to show you everything, but I'll pick a few samples here. So this is an example. Make the type a little bigger. Yeah. Make the window bigger too. Okay. So this is what the raw dependency data looks like in JSON form, and this is. Let's see, this is at the method level, right? So we're seeing entries that have things like def and init, right? So this is the constructor. This represents the dependency graph. There's two types of edges. There's extends edges and uses edges. Uses covers all other kinds of references that you can have. And we see that this includes dependencies on external code as well. So it'll show you what you're using from your whatever's on your class path, including the Java and Scala standard libraries. The method level data is voluminous and hard to deal with without tooling, which doesn't currently exist. So I think that you will most often want to use the option that that aggregates the data at the class level, and then maybe if you became interested in a particular edge, then you might flip over to the method level data to see where that class level edge is coming from. Okay, so I don't think I'll skip over this stuff about the case classes and memory. Yeah, so here's what the layers and cycles reports looks like. So this is the layers report for a really simple piece of code that just where's the code for this? This is just two object definitions that refer to standard library stuff. So all the standard library stuff ends up in layer 0, and then your user code is in layer 1. This is an excerpt from the layer report that I ran on a codebase of my own. And let's see. So the one on the bottom here, this is the layers, and this is what a cycle looks like. So this is saying I have these 8 classes that are all mutually entangled, and here's the names of those classes. There's some stuff where you can modify you can actually delete edges in memory and then see how the report changes. I'm not sure if that's useful or not. Question from Will.
Does this pick up on things like f-bound polymorphism and so on?
The question is, does this pick up on things like f-bound polymorphism? Because this is source code analysis and not bytecode analysis, it will pick up stuff that's only in types. Is there something special about f-bound polymorphism in particular that you're curious about, or is it just that it's like stuff that only exists in the types?
It only, how smart is it, I guess, is the question, which I think you just answered. It reports things, but it doesn't know that it's that relationship.
Does it classify the relationships? No. Yeah. Okay. So I'll flip back to the slides now. Of course, there's all sorts of directions that a tool like this could go, and all sorts of features that it could have or should have. I'll just mention the most obvious missing features, in my opinion at least, is that I think you would really want something that can that can aggregate. So method level is the raw level. We can aggregate at class level. We don't have code that supports package level or source file level aggregation. I think if someone wanted to add that, really wouldn't be terribly hard. I said this already, but I'll say it again because I think it's important. Anything you want to do with this data, you're not up in compiler guts. It's just simple data. Okay, so we covered the maintenance status of Sculpt. Are there any? I should pause here. Are there any questions about Sculpt in particular? Yes.
What are the performance implications of using this as part of the compile? It's a compiler plugin. Does it slow down by a factor of?
Okay, so the question is, does adding this to your build, is this going to slow down your build if you enable it? So I have to admit that I haven't measured that. I would expect that any slowdown would be negligible. So, or if not totally negligible, I can't imagine how it could possibly cost you more than like 1% or 2% or something like that. I would expect it wouldn't even be that high. It really, the ExtractDependencies code is really not doing can't say none. It does very little additional traversal of your code. It's mainly just recording information that already exists within the compiler. It doesn't have to do a lot of work to get this. Any other questions on Sculpt? Yes, Will.
So it sounds like it's a reporter that's extracting Zinc information. If you're using it in SQT and you're running it, then it only reports what's incremental about it. So if you run it the first time and then you run it the second time, it's only going to pick up on whatever you have incremented from the first run.
Okay, yes, great question. So the question is, if what happens if this plugin is enabled when I do an incremental compile? What happens? So the answer to that is, don't do that. That's not the expected use mode. The expected use mode is that you would generate this data once from a clean compile. I mean, it's a question I hadn't considered before. And I think it's entirely I would expect that you would get accurate information out of the follow-up incremental compiles. You would just then be faced with the problem of how to combine the data that you got from the full compilation run with the new data that you got from an incremental compile. The logic for combining those doesn't exist. But I don't, in practice, I don't, I think this is the kind of thing where it's kind of like development is paused. You do a full compile, you get this information out, and you go off and analyze it. I don't envision this being used in tight incremental coding cycles. Yes, Will.
I just give you information on the use case. There are times when people will change something on the routing file in play, and they will immediately complain that it took incredibly long for everything to be built. Why did this happen? And the answer is because you just changed something at the very base of the project, and it's got all these cycles inside of it, and the compiler is spending all this time trying to work out what the hell happened. So as a reporter for SPT compiler information, it sounds useful already, whether it's incremental or not.
I see. That's. I'm really glad that you said that, because that's. Okay, yeah. So I get it now, and actually, yeah, that's a great use case for this. Why didn't I think of that? So let me repeat what Will said. In the course of this talk, I've been envisioning this as a tool where you're looking at your code base as a whole and trying to, just make improvements to the dependency structure. But Will's question is, suppose I just it's like I changed something in my code, in a play routing file, for example, and this really long incremental compile followed, and that was unexpected, and I'm unhappy about it. And can this tool help me analyze what happened? I would think that the report that you would get out of the plugin on that incremental compile would it would have only the information that you wanted. Great idea. It would have to actually be tried in practice, but I think that would work, and that might save you quite some effort, sort of disentangling the part that you care about from the big picture. Anything else on Sculpt? Okay. So we're almost done. I would just want to mention a few more tools that exist for. Okay. So to wrap up on Sculpt, I guess. I'm not. There we go. Okay. So I've presented this thing that's incomplete. I think it's possible that some projects might actually find it usable and useful as it is. I'm not sure. We just open sourced this last month, so we don't have information on that. There's been interest, but I don't know if anyone is actually out there trying it. But even if you this is like too primitive for what you want to do, I'm also putting this out there in the hopes that it could be a basis for either building your own tooling, or either for your own use or for use in the community. Okay, so a couple more tools to mention, and then I'll be done. These are tools that I actually don't know very much about. So IntelliJ includes this thing called the dependency structure matrix. Has anyone used this? Can you raise a hand if you've used this? Okay. So this is a commercial feature, and it's only supported for Java, which is why I won't spend too much time on it. It looks pretty amazing, or pretty powerful, and also potentially incredibly confusing, right? There's a whole manual section in IntelliJ that explains what all this stuff is. It's like the rows are this, the columns are this, you can expand stuff. It looks like a great tool for really digging into the structure of your Java code. So I'm including it, on the off chance that you're maintaining a Java code base that you want this kind of thing for. I also mention it just because, if you're building this kind of tooling, it looks to me like you could look at this and get a lot of ideas for data that a tool like Sculpt could be. Analyses that it could be doing. I'm not totally surprised that no one's used it, though. Okay, and there's we found out after we built Sculpt that there had been an earlier project called Extractor that looks very similar. I haven't had time to look into it. It hasn't been touched in the last 2 years, so this is probably only of interest if you're interested in building this kind of thing yourself. Okay, some closing thoughts on how to keep your code clean once you've cleaned it up with these and made it more modular with these techniques. The biggest hammer that you can use is to move code into separate repos. At that point, reintroducing these compile time dependencies becomes impossible. The slightly smaller version of that hammer is making subprojects in your build tool, and that also makes unwanted dependencies impossible. So if I tell it, if I put stuff in separate source directories and tell SBT which subprojects I expect, or not just expect, but allow to depend on each other, then code that goes outside that structure just simply won't compile. So if you can do that, then you're good from that point forward. If you do make a tool like Classycle or Sculpt part of your build ongoing, I'd strongly recommend doing that as part of CI. I had a great experience with that and Classycle. And one closing thought: if the tooling that you want doesn't exist, consider building it. So I said I had this great experience with Classycle, but actually it really didn't do exactly what I wanted, and I could easily have given up at that point. But I did some custom work on actually doing code generation on a Classycle config file. So the config file that I wanted, involving recursive dependencies between packages, like writing it by hand would have been essentially impossible. But it was not that hard to write a little code generator that could expand the rules I wanted to write into the rules that the Classycle can write. And even though the code that I built for that was only ever used on this one project, it was totally worth it. Okay, so I have a couple questions for you in the audience. Are there, you know, when we were doing the preliminary research on Sculpt, we tried to find out about everything that's out there that's kind of in this space. Did we miss anything? Does anyone here know of something that like would have logically had a place in this talk? Yes, Will. JDEPs. I've never heard of JDEPs. What can you tell us about it?
That is the Java module system in Java 9.
Ah, okay. So this is the former Project Jigsaw. Are we talking about? Yes. That's totally relevant, and the reason I didn't include it is that I know almost nothing about it. But yeah, that's a great point. Like, there should be a slide on this. Like, you know, Jigsaw has implications for this. I mean, so right. So you know, I do know that Jigsaw actually involves specifying metadata for your modules that like specifies what's exported and what's not. So it's like more levels of access control beyond just whether something is public or not. And there's enforcement. Like you can, if you enable the enforcement, then you know code will refuse to compile or refuse to run if it violates these module boundaries that you set up. So yeah, thanks for bringing that up. That's totally relevant.
Just remind me the first define code tool you used. The first one covered.
Classycle?
Okay, thanks.
Yeah, it's a little hard to spell. It's like how many? Where are the S's and C's in that? It's here. So that's the URL. It's on SourceForge, which tells you how old it is. But it was updated in 2014 for Java 8, and yeah, I really recommend it. Okay, that's all. Thank you.